Hi folks, welcome back to Physics with Captain Rod. I'm going to spend some time here talking about problems 15, 16, and 17 here on the Unit 5 homework over magnetism and induction. Alright, well first of all let me talk a little bit about magnetic flux. Hopefully you've seen my previous video, the one about the solenoid and how, the one about AC power and how AC power is generated by taking some sort of current loop and rotating it in a magnetic field. And what that does is it induces a voltage on the loop via that QVB force. And then I made a video about Faraday's law of induction where I take a solenoid and talk about how the voltage is related to the flux. So again, I want to talk about why is this quantity flux so important? Because the voltage you get in a current loop is equal to the rate that the magnetic flux changes. So it's equal to change in magnetic flux over change in time. So it's important just conceptually to realize that anytime you change flux, you will get a voltage in a loop when you change your magnetic flux, where the magnetic flux is the field strength times the area. Now it turns out when you calculate magnetic flux, there's a third part of the equation here. This reads times cosine theta. That's called a trigonometric function. Trigonometry is not a super important part of this course. This course is intended just to be kind of conceptual in nature, but let me talk about how that relates here. So the flux depends on the orientation. So imagine this loop that I have here. So imagine this being kind of a hula hoop, and I've drawn some magnetic field vectors there. And you'll notice that several of the vectors go through the hoop. So in this orientation, we would have a magnetic flux through the surface. Now, if I rotate it so that the hoop is like parallel to these vectors, then they're not really going through this area and we don't have any flux. So conceptually here, that's what this cosine theta would take into account. Right? For our purposes here, we just need to recognize when flux is changing. And one way to change the flux is if we take this and rotate it. Again, see how as this hoop rotates around, the flux is a maximum in this orientation, and now it's 0, and now it's a maximum right about there, and now the flux is 0 right about there. So anytime the hoop is like this or like this, the magnetic flux is a maximum. Anytime the hoop is like this or like this, the magnetic flux is basically 0. An important thing to realize is anytime we are rotating like this, the flux is changing. And what that does is it introduces a voltage in this current loop here. All right, so that's why flux is so important. So number 15 here, where it says, let's see, find the flux of the Earth's magnetic field of 5 times 10 to the minus 5th teslas through a square area of 10 centimeters for the following. Okay, so I actually got to get rid of this. I'm going to move this out of here and get rid of it because it says square. So imagine a square. I'm going to draw the square kind of like this. Okay, and it's 10 centimeter square area. Now, they've already given an area of 10 square centimeter. This needs to be converted to square meters. And remember that there's 100 centimeters in 1 meter. But when you square this conversion factor, you get 10,000 square centimeters in 1 square meter. So this is what you want to use as your conversion factor to convert this to meters. Now, part A says when the field is perpendicular to the plane of the loop. So I believe what they mean by that is, let's see, when the field is perpendicular to the plane. So I think they mean in orientation basically like this. And that's where the flux is equal to field strength times area. It's a maximum. I'm going to skip part B for just a minute. Part C, when the field makes an angle of 90 degrees to the with a normal to the plane. When the field makes a 90-degree angle normal to the plane. So now they mean this. Normal to the plane. Normal is just a funny word for perpendicular. So what they mean, normal in this picture would basically be up. And 90 degrees, this would be when the normal makes an angle of 90 degrees to the field. This is the orientation that they're talking about. And now you'll notice that the magnetic field vectors are basically parallel to this area, so now the flux is 0. Okay, part B. I'm not going to hold you folks on a quiz or a test responsible for these types of problems here in part B. I'm just going to tell you how to get this one done so that you can get your homework points on it. So now, to get part B, where it says when the field makes a 40.5 degree angle with the normal to the plane of the loop, just put the magnetic field given here, the area given here, and on your calculator you should see a cosine function, and just put in times cosine of that angle given, and that will allow you to get the your answer for part B. And when I test you on this stuff, I'm not going to give you anything that's got any sines or cosines or any math that's not a prereq for the course. Some of the concepts that I'm trying to put that need to be in the class are just above the math level that I thought was appropriate for the prereq. I still pick problems that are kind of in that region, but you know, in cases like this, I'm going to make it so that you can get your points, but I'm not going to hold you responsible for knowing anything about trigonometry on your quizzes, so don't worry about that. The important concept here in this problem is recognizing that in this orientation, the flux is a maximum. In this orientation, the flux is 0. So again, see how like this vector is parallel to that surface, so none of it goes through it. All right, and that should be enough on that problem. All right, number 16, it says a circular hoop with a radius of 11.6 centimeters is placed in a magnetic field. All right, so I'm going to get rid of this stuff. Okay, a circular hoop. So I'm going to use my tool here, right? There's some sort of circle. So this is kind of like a hula hoop looked at kind of like from the side with maybe this edge kind of coming towards you. It is placed in a region where there's a magnetic field of 8.5. Oh, I'm sorry, wait a minute. Let's see, if the field is directed perpendicular to the plane, okay, so I'm going to draw magnetic field vectors that are this way. And the reason this way is they said perpendicular to the plane. So basically what that means is, like if I backtrack that vector, it means a right angle to this thing's surface. And it says the flux through the hoop is 8.5 times 10 to the minus third Tesla meter squared. Now your value may be something else. That's what mine says. Now the important thing to recognize is that this is a magnetic flux. You can tell by the units, Tesla times meter squared. And remember, magnetic flux, that's what this symbol means, is equal to magnetic field strength times area. So in this problem, this value is this number right here. Now they also told us the radius of this. In my example, it says the radius is 11.6 centimeters, which would be 0.116 meters. The area is the area of that circle, which is pi r squared. So you can calculate the area by taking this value here. Once you calculate the area, that number will go there, and that'll allow you to calculate the magnetic field strength. Part B, it says if the magnetic field is directed parallel to the plane of the loop, what will the flux of the loop be? All right, so that's a conceptual question. And I'm going to draw this where it says if the magnetic field is parallel to the plane of the loop. What they mean by that is this. The plane of the loop is such that it's parallel to these magnetic field vectors. So these field vectors now, see how they don't really go through the area anymore. So that should allow you to take a good guess at what the flux is. This is just a conceptual question. There's no calculator there. All right. 17. Let's chat about 17. So 17 is about Faraday's law of induction. Hopefully you've seen my video about Faraday's law of induction. But let me just kind of review it quick. Anytime you change magnetic flux, you create a voltage. It's called the induced voltage. And the induced voltage is equal to the rate that the flux changes. So it's change in flux over change in time where the flux is equal to the magnetic field times the area. So in number 17, they show a circle, and it's a round circle, so and then they show a bunch of vectors like this. These vectors represent magnetic field vectors that are pointing away from you, like they're pointing in the direction that your eyes are pointing as you watch this video. All right, so these represent magnetic field vectors. And it says the magnetic field strength is 0.18 teslas. That's in my example. Yours might be a different numerical value. All right, then it says somebody grabs the loop at A and B, and they pull on it until the area is nearly zero. So what they're talking about is, imagine they grab this and they pull on it until basically it's really long and thin, like this, but it has almost no area. So if it doesn't have any area, now it's not going to have any flux. So we can calculate a change in flux by calculating the original flux, which is going to be this magnetic field strength, times the circular area, which is going to be pi r squared. And these are values given in the problem. So that's the initial flux. The final flux is 0, because if it says right in the problem, basically it's stretched to the point where it has no area. So now whatever this number is, that's going to represent your change in flux. So the induced voltage, we're going to take our change in flux, that's going to be this value, and then you're going to divide by the change in time, which was given in the problem. So that should be enough to calculate a voltage there. Again, conceptually, it's important to realize anytime you change a magnetic flux, you're going to create a voltage. So I think that's enough on this video. I hope it helps get those homework problems done. Have a great day.